Good then. Okay, so this is a talk. I'm going to try and rush through it. We're a bit short for time this session. So this is just going to be a talk about process injection, kind of a quick overview and a bit of a whirlwind tour of it. The boring slide about me. I'm Keith. That's my Twitter handle. I am an Abertay graduate. I left in 2016, which is a surprisingly large amount of time now. I worked in SOC for 5 years, and I spent the last year as an IR consultant, and I also have hobbies that don't relate to this talk. So, process injection. It is MITRE tactic 1055, and if I think I've got the tab open, it's okay. Well, it's not showing, but the page has 15 different subcategories, and the examples they list, there's about 50 of them, different groups and different malware that use it. So it's a pretty ubiquitous technique these days. Used in most common malware and red team toolkits. Anyone in the previous talk would have noticed pretty much all of the frameworks he mentioned, all of them had process injection modules. So in some threat intelligence reports, this is one CISA did for Quackbots. It mentions it injects itself into legitimate processes to avoid detection. Here's one from Red Canary for the iced ID Trojan. It also says that it hollows out a process and injects into it. All these reports, they kind of brush over the idea of injection as established knowledge, something that you already know. And that's fair enough, because if they had to get into bogged down in details on every step, the reports would be never ending. So basically the idea of process injection is being able to run code in the address space and context of a different process, usually a legitimate one. So first of all, I'll go over processes and how they are formed in Windows. So generally, it's a single instance of an executing program. That's what a process is. This is just a picture of Task Manager from my computer. You'll notice that it looks like a list of executable files, but near the bottom there's NV display container. There's 2 copies of it, so it isn't just a list of executables. It's essentially a container for the resources being used. And these are the resources being used. The process is made of a unique numeric ID, which is the second column there. A program, just executable code. Usually that's the executable file itself that's getting loaded into memory, but it also constitutes any DLLs, any libraries that the process loads in. A private address space, it has a chunk of memory that belongs to it. There's a security context, which is an access token that explains the user running it, the privileges they have, security groups, or whether they've set the UAC so they're running as admin, that sort of stuff. There's a list of open handles, which they're flags showing which resources the process is using. They're the entire talk of themselves, so they're not important for this talk. And at least one thread. Threads are the important thing here. So the next slide is a thread is listed in the Windows internals book as the entity within a process that can be scheduled for execution, which, unless you know what it is, doesn't really mean much. It's the thing that is running the executable program. You have code from the executables and DLLs to execute. The computer has physical cores that work one action at a time. A thread is essentially a virtual representation of that. It's how it's managing the resources, of dividing up, how the operating system divides up the tasks that needs to be done. There is multi-threading. The last slide said at least one thread is in a process. Processes can have multiple threads that run in parallel, and you can assign more or less during runtime as needed. And you make threads with the create thread function, which really only takes a function pointer argument, which just says, where in this executable code am I going to start? If you have the permissions to create a thread, you can put one in at a point in the code. And there is a function called create remote thread, which is similar, but has the quality that you can create a thread in a different process. That's an important idea here because process injection is a Windows functionality. It's not solely an attack. It's a Windows functionality that attackers abuse. So why? Why would you do process injection? The main reason is for defense evasion. You've got execution coming from what looks to be a legitimate application. What actually is a legitimate application, just doing malicious activity. Here's a picture from something I stored in 2020. You can see that the code is coming out of spoolsv.exe. That's the printer spooler executable. So what you've got there is the printer spooler seems to spin up a command prompt and run some encoded PowerShell. It's not just for confusing humans. It does confuse humans when they see these weird process trees. But it's good for evading antivirus and EDR protections. Even EDR that are set up to detect process injection, if they have functionalities that are like process disruption, if I see something bad, stop it, a lot of them are going to balk at the idea of stopping a legitimate Windows executable in fear of breaking the system. So here's a picture from, I think it's a Fortinet thing about Quackbot. And what Quackbot was doing was it was searching for known security tools on the left. And if it found one of those executables running, it would inject into a specific target that it knew was whitelisted by the security software. So if it found the host was running Sophos, it would inject into a copy of MobSync, which is some relic of Windows Mobile. Other reasons, privilege escalation. It's not as common an issue these days because Windows has, over Windows 8, 10, and 11, moved more towards the sort of least privilege model. Things will run with the least privilege possible until they need more. Because the idea was if you could inject into a process with higher levels of privilege, you would then have access to those privileges. An example there was one of the Metasploit modules for Windows 7, a way to get around user access control, UAC. It would inject into a copy of explorer.exe, which is a binary that is signed by Microsoft. It has a signed Windows certificate, which UAC doesn't trigger for. And exploitation. Once you are injected into a process, similar to how you get access to the privileges, you get access to whatever the memory and resources that process has. The big one, I didn't put another bullet point in there. The big one there is LSAS. Traditionally, to steal credentials from LSAS, which is the executable that runs basically all the Windows authentication stuff locally, you would do a memory dump of that and then use a tool like Mimikat on the dump. But if you can inject into the LSAS process, you don't need to dump the memory. You can just read it live, and that way you're not putting anything to disk. You're not putting that memory dump to disk. However, for things like that, you do need high privileges. Not anyone can just inject into LSAS. You need to have the highest of high privileges. So it's usually a later step in the attack chain. So here's some examples of injection and how they actually work as a sort of high-level abstraction. Classic DLL injection, when this was first sort of becoming popularized, this was a more common method. Here are my wonderful MS Paint diagrams. So what you would do is you have your malicious code that is running, whether that's from a macro in a Word document, whether that's remote code execution, whatever. You would write yourself a DLL with all your malicious actions you want to take, or malware, all in a DLL, so it's lovely Windows executable code. And then you have a target process that you are wanting to inject into. It's sitting there running happily with its legitimate contents. So First of all, the malicious code identifies the process it wants to target, and then it uses a function called openProcess, which gives it a handle. Essentially, it gives it access to this process, and thus the memory. You use virtual alloc, which was mentioned in the previous talk. This is a function that just allocates a chunk of memory. Now, if you have opened process successfully, you can now allocate a remote chunk of memory in the target process. Now, what you do with this is you allocate a chunk of memory big enough for the address of your DLL. Wherever your DLL is in memory, you put that address into the process. And then essentially there's a function called load library. You create a new thread with the create remote thread function I mentioned before to use the load library function against the address you've just written, at which point the new thread that comes into the process says, okay, my job is to load this library into the function and start running it. And all your malware, rather than sitting in a DLL on disk, is then pulled into the legitimate process and starts running. This isn't particularly stealthy. It's still used because sometimes, people don't care about stealth because it works. If you get caught, it doesn't matter if you've got in and out fast enough. It doesn't matter if you get caught if you've already done your action. Writing the DLL to disk gives the antivirus a chance to see, oh, something bad has landed on me. I'll delete it. But if we're already writing something to the process, why don't, instead of writing the address to something on disk, why don't we just allocate more memory and write our malware into the process? The reason is your code will have absolute addresses. There will be, commands in there that say jump to this memory address. If you copy your malware into memory, you don't have your process in there. You have a copy of the process in there, which will have different memory addresses. So what you would need is what's called a relocation table, which is part of all processing windows, which essentially, if you move a process in memory, it translates all of these absolute addresses in memory to what they should be. But if you're just copying it into a process, it's not going to do that. You need to manually reach out to the relocation table and change those addresses. So reflective DLL injection takes advantage of a thing called reflective programming, which is the ability of some programming languages to examine itself during runtime. For example, if you wanted to return if you had a variable in code and you wanted your program to return what type of variable it was, say you had an integer and you wanted to return, this is an integer variable. The code isn't going to be able to see that from inside the runtime. It has to look at the process as a whole to understand these sort of metadata ideas. So, as I kind of went over, you are opening the process, same as before, virtual alloc, same as before, except you're writing a big chunk of memory. Yes, thank you. Your battery's running low. So what you do is you are writing the DLL into memory. It's unloaded because it has all these incorrect addresses. And you have a little chunk of code that is the reflective loader. This is going to sort all those problems and load the DLL into memory. So the loader code, you create the remote thread and point it at the loader code. It calculates its own location in memory and then allocates another chunk of memory. It then copies the DLL into that, so you have another copy. From there, it knows the chunk of memory it's in. It can find the relocation table through the reflective aspects, and then translate all the addresses in the code so it can finally run your malware. And this is sort of the Cobalt Strike bog standard, this is how they are loading all of their individual modules in whenever you are setting them off. I'll skip over the picture of that though. Process hollowing is favourite a lot of the malware rather than these toolkits like Cobalt Strike, your quack bots, your trick bots. Okay, it's dead. Is there a pen here? Is there a pen? That's a big, so I'm not writing on a whiteboard with that. I'm just wondering if there's a pen for the whiteboard. I'll check down this one.
Find something?
Yes. So, let's see if I can remember the steps. So the idea is you have your malicious code, you have your target. I'm just making sure everyone can see this, right? Okay, you have your target process. You have sort of the legitimate code that's running. So the idea of process hollowing is that rather than looking for an already running application, if you just create a new instance of it, you don't need any of the legitimate stuff. So you create the process, your malicious code, open the process to get a handle to it, and then it uses a function to unmap all of this memory. So essentially, you are hollowing it out. You're removing all of the legitimate application, but you're keeping the shell that has the privileges, that has the name in the Windows operating system that's running. It still thinks it's Calculator or Notepad. You then, same as before, you write your own malware in here, and similar to the reflective stuff, you need to translate all these memory addresses, and it's a very similar process to the reflective DLL injection. But because you're writing directly here, you just have to find the relocation table and have a bit of shellcode that manually tweaks all the addresses. What was the next slide? I'll go over some identification instead. So you have these things happening. If you think something's gone wrong, how are you going to be able to ID that thread injection has happened? So with the classic DLL injection, it's not too complex to find out. Each process has what's known as an eProcess block and a PEB that's associated with it as well. I can't remember what PEB stands for offhand. It was in the slide. But that contains a lot of metadata about the process, and one thing in particular is the PEB block has all of the DLLs that have been loaded in and their memory addresses. So if you have a load of System32 DLLs loaded and one that's in, My Music, it's a bit interesting that, a big chunk of DLL library has been loaded from a random place. That doesn't really work for reflective injection, though, because the DLL doesn't exist on disk, so it can't be mapped into the table. But then you have the idea that absence of evidence is evidence of absence. If you have a DLL that is in the code that doesn't map to anything on disk, then where did the library come from? You can put a gun anywhere in a suitcase, but when it goes through an X-ray machine and the gun silhouette shows up, you can identify it. We know what DLLs look like. They have the same header as executables. They all fit the same function. They all fit the same format. So if you look for that within a process and then try and map it to known DLLs, you can identify anomalies. On a similar note, executable memory in a process. All memory has, whether it's read, write, executable, or a combination of them. If you have executable memory in a process that doesn't map to known executables or known libraries, why is it there? Why is it executable? Why is there stuff executing in this process that the computer doesn't know about? And on a detection front, I mean, those are great for identification if you're sort of an instant responder looking at things. But as far as detecting it proactively as an EDR goes, it's not great. Most of the detection revolves around those functions that I was mentioning, create remote thread, virtual alloc-x, things that allow you to allocate memory in a remote process or to create a thread in a different process. Windows has a thing called ETW, Event Tracing for Windows. There's an entire talk, hour-long talk in and of itself, just to discuss all the things that can do. But generally, it's a logging system that generates application-level stuff down to kernel-level stuff, just what is happening on the operating system. And one of the things it can do is identify when these remote calls are being made. EDR tends to do a similar thing, but they use their own sort of home-built moonshine ways of doing so, usually using Windows hooks. So the idea is that you call create remote thread, the antivirus goes, or the EDR goes, hey, come to me first so I can check what you're doing, and then I'll forward it on, at which point that's usually when EDRs with protection abilities sort of disrupt the chain. I think one of the big caveats to go over in this is anyone who's worked with Windows for a long amount of time will know that there is no one way of doing things in Windows. If you have create remote thread, there's going to be at least 5 undocumented function calls that do the same thing. So these hooks that are looking for certain calls aren't entirely reliable because there are different ways of doing it. And as Kieran in the last talk mentioned, you can even write your own sort of homebrew strips of shellcode that do a lot of the same steps and can call load library or virtual alloc-x without it showing up in the Windows traces because it's sort of directly accessing rather than a standard call. There was a conclusion slide, but I can't remember what was in it other than process injection is a thing. So, yeah. So there's a brief whirlwind tour just to give you a bit more of an understanding of what these threat intelligence reports brush over. But what's time? You've got 1 minute before lunch. Does anyone have a question? I'll go to you next.
Can I ask you about the identification bits when you were talking about mapping or trying to map a digital DLL that is in memory to known DLL? How much is that impact performance in the program that is returning live?
This isn't something that you do continuously. It's not great for a detection method because it's less the action takes up resources, but more how often would you check? It's good for sort of dead disk, if you get a chunk of memory dumped from an operating system and someone says, something happened on this machine, please help, I don't know what to do. Yeah, you can ask me up here whenever it's lunchtime.